let's get started. Welcome. Thanks for coming today. So, anybody have any comments or questions about Peter's talk on Thursday? Was there any? Yes?
So does he sell most, like license and sell most of his designs?
Some of the stuff is commercially available, some he licensed, and I think he makes a lot of money from small business innovative research grants, and he also does a lot of testing commercially, and he's very active in standards. So, I mean, if you're building a wheelchair, how do you know that it meets a standard? It's quality. So there's a whole organization that tests not only wheelchairs but scooters and every other possible thing, and it's international. And he manages a lot of that stuff, so he's a busy person. Well, there's other people there that help him. So, but I know initially he got a lot of small grants to get going on that. Any other comments? Anything that really impressed you or you found interesting or new or surprising? New perspective? Well, one thing that I wanted to mention is that he really brought out the need of when you have a product, how do you measure its performance? How do you know? How can you advertise that your product is as good as or better than somebody else? Well, you have to measure it, and to measure it, that's a whole nother activity. Now, you guys aren't going to be doing that kind of stuff. You're just going to be doing the prototyping in. But beyond making a device, you have to test how well it works. You know, when is it going to fail? And things like that. So that's requires a lot of measurement, and also this kind of measurement is used when you do research. When you come up with a new idea for something, you maybe build a device and measure how well it works compared to existing devices. So this measurement aspect is really critical in a lot of places, but we're not focusing on that here. Okay. Anything else? All right. Move on. So we got our attendance sheet, and one new thing is the sign-up sheet for student passengers for the tour of the VA next Tuesday. So same kind of sign-up. I'll send you maps, and I'll send you emails and stuff about who's in what car and everything like that. But make sure you sign up either today or Thursday. It's for students only, so we just don't have a whole lot of room there, so students and drivers only. So that's good. So here's what the sign-up sheet looks like. If you're driving solo, if you're a student that's driving solo from home, let me know so I can send you a map so you'll get there. Okay. And we have the sign-up to meet with Dave sheet. And that's really working well. Met with all the groups multiple times. And I just want to reiterate that people working on projects, both teams and individuals, it would be good for you to meet with me periodically and send me emails to report your progress. Anything that's a success, I'd like to hear about, because I know that you're really working on this stuff. Okay. I want to mention one thing in your work is that you should not be stalled waiting for another person to do something. Other people are on their schedule, you're on this quarter schedule. You can't say, well, I'm waiting for this guy to get back to me, or I'm waiting for this part to come in. You should be working all the time, independent on what's happening. So you shouldn't be blocked by any one event. You should have a backup plan. You should be working on something else. There's a lot of stuff to work on. So don't stop working because the next thing in the sequence isn't happening. You need to be working all the time. Okay? So the midterm project presentations are a week from Thursday, the 12th, and as I mentioned, teams are getting 8 minutes each, so that's a really fair amount of time for you to make a full report. Midterm reports are due the Tuesday after the presentations, and you can refer to the handout that you got on the first day of class, or it's also online, on the important elements of your presentation, and I'll also send out some tips to you on Friday. So it's really important to practice your presentation to make sure it's within time, it flows correctly, and the more you practice, the better it's going to be. And it's extremely noticeable that if you practice, it'll be much better than if you don't, it's going to be lousy. And it's just so obvious when people haven't practiced. So I really encourage you to do that. So I thought it'd be a good point to go over the perspectives that we've had so far in the class. We talked about, there's me. We had a perspective of students with disabilities, and students with disabilities is over here. We had people pitching projects who themselves had a disability or work with people with disability. We had Gail talk about interview techniques. We had a software engineer talking about exoskeletons. We had Fernanda talk about her perspective. We had Olenka at the playground talk about access to playgrounds. We had Peter talk about his perspective on accessing sports and stuff like that. And today, Professor Okamura is going to talk about some of her work as a researcher. And on Thursday, we'll have a prosthetist talk about his view of challenging prosthetic devices. So, and then in the future, a lot of other different perspectives. So this word perspectives really comes into play a lot. So Thursday, Gary Burke, he's a prosthetist that works over at Stanford, and he has his own business. So he's a really excellent person, and he's been involved in the course for a long time, and he gives a great talk, so you don't want to miss that. But today, Professor Okamura and I will talk about rehab and assistive robots, and we'll take a short break while we get Professor Okamura set up. So if you haven't signed up yet, do that now. Turn this off, actually. Yeah, I'm turning this off and removing it. Microphone when you have a chance.
That's new, right? I don't remember being microphone. I do. It's over here. Maybe I'll take this out. This is not good. Okay, how's that?
Okay. Let's start up again. Dan? It's my pleasure once again to have Professor Okamura. You're giving a talk on rehab robotics. She received her bachelor degree from the University of California at Berkeley, which we long hold against her, and MS and PhD degrees from Stanford in 1996 to 2000 in mechanical engineering. She's an associate professor in the mechanical engineering department here at Stanford. She was previously a professor and vice chair of mechanical engineering at Johns Hopkins, and she's been an associate editor of the IEEE Transactions on Haptics and editor of the IEEE International Conference on Robotics and Automation, and on the editorial board of the Automation Conference editorial board, and co-chair of the IEEE Haptics Symposium. She's worked in IEEE physicians for the last 10 years, and she's an IEEE fellow. And her interests include haptics, which she teaches a course in, teleoperation, virtual environments, simulators, medical products, mechanics, rehabilitation, prosthetics, and engineering education. So let's welcome Professor Okamura.
Hey, thanks. Thank you, Dave. And actually, it's fantastic to see so many familiar faces here. Some of you have worked in my lab or taken other classes with me or interviewed me. And so it's great to see everybody. Maybe one quick note of advertisement. If people are interested in medical robotics, more on the surgery side, I actually teach a class next quarter on medical robotics. And if you feel like you don't have the prereqs for that, there's also a one-unit seminar, which is every Friday at 11 a.m. There's a one-unit seminar version where we have speakers from academia and industry come in and tell us about the state of medical robots. So different from the kind of medical robots I'm talking about today, there's be more on the surgery interventional side. So with that advertisement done, today I want to talk about rehabilitation or movement therapy robots. And these apply to a lot of different patient populations. Stroke being the big one. There's hundreds of thousands of stroke cases every year, and it has a huge economic impact on our country. And as we'll discuss a little bit more later, it's also very difficult to treat or to rehabilitate from because of the fact that every patient is different, and it's even difficult for therapists and researchers to understand what the deficits are. But this has a huge impact, and that's an area in which I'm working now. Cerebral palsy is one with a lot of prevalence. There are some really terrific researchers here at Stanford that work in that area. And while there are many, many others, the other I thought I'd note up here is various orthopedic inventions or interventions. So either recovery from injury or issues that come from birth. There is a lot of rehabilitation that goes into impacting recovery there. And I should note, I did give these slides to Dave, and so you have all the slides available to you, so you don't need to write a ton down about this material. So stroke being the biggest thing here, I want to talk a little bit about what are the type of deficits that we see, and then the variables that are considered in optimal rehabilitation. So in stroke patients, you often see loss of limb function as well, and that is like motor capabilities in terms of either making reaches. Sometimes they have issues with synergy, where so many joints become kind of coupled together in their behavior, and it's hard to decouple them in order to make the movements that a patient desires. And in addition, there can be sensory loss as well. And so one example I always like to talk about is the ability to have proprioception, which is knowing where your own body is in space. And a lot of things can affect it, but let's actually do a little quick exercise just to give you an example of proprioception and what it might be like to lose it. So everybody raise your hands above your head, and without looking at your hands, point your fingers together and then touch the fingers together. Okay, so you might have missed the first time, but eventually you got it. Okay, you can put your hands down now. So our proprioception is not perfect, right? Proprioception is your sense of self, and if I knew exactly where my hands are, I could probably get the fingers to touch each other. But as a matter of fact, it's not perfect, but it's still pretty good. And a lot of stroke patients, as well as people with diabetes and other sort of deficits, they lose that sense of proprioception. And so if you don't know where your self is, it makes it even harder to create movement. In fact, there are patients with large fiber sensory neuropathy who can almost do none of the activities of daily living, and very, very difficult to walk because they don't have that sense of self. So anyways, the combination of when you have a stroke and the parts of the brain that are damaged and have blood loss or lose oxygenation makes it so that you damage your motor control capabilities as well as your sensory capabilities. And so when people talk about rehabilitation from stroke, a lot of it is trying to recreate neural pathways to replace those that have been damaged. So there'll be one part of the brain that maybe was responsible for motor control of the hand, and if that part was damaged, you have to see, can you create other neural pathways that actually can allow people to recreate that motion capability in the future. And that requires practice. And so a lot of rehabilitation has to do with doing things over and over again. So quantity is important. So being able to make movements in the right way, in the desired way, many, many times. How long you do it for and how long is a particular session is something you have to define. And then how intense is, say, a particular workout, particular practice. And then also, is it task specific? I think this is almost a fundamental question in neuroscience, is how useful is it for you to sort of generally just make the same movement over and over versus making, say, a reaching movement to an object. And so there have been some studies showing that, well, you can do all of these things here, but if you don't connect it to a task, maybe the neural circuits aren't actually reconnected in the same ways, and so it can help to do functional tasks during rehabilitation. So how can a robot help with this? I mean, obviously human therapists are employed to actually help people recover from these kinds of deficits, and why bring a robot into this situation at all? Well, I would say the early work in rehab robots, the idea was just to take what human therapists did and try to just apply those strategies to patients. And in part because robots have different sensory capabilities, they have a different level of understanding of the patient, most of it being much poorer than what a human therapist would have, those strategies weren't very effective. And in fact, there's been many rehab robotic studies that have been done that show that rehab robotics is not as effective as a human therapist. But as we start to understand the deficits better and understand why human therapists do the things that they do and what things human therapists actually just can't do, then there's the possibility that robots can contribute more. And so they can do a few different things. So assisting movement is one possible control strategy. So if I want to move from here to here, sorry, drop some cookies. If I want to move from here to here, the idea is a robot could help me move my arm the way it should be moved. Okay, so you might think, well, that is not so much a rehabilitative strategy as an assistive strategy, right? So if you could say, well, if someone wants to move their arm from here to here, isn't it better to try to get them to move it themselves? And generally speaking, that is true. And so assistance can actually slow down recovery at times. However, for certain types of deficits or at certain stages in recovery, there's what's known as, in neuroscience, as Hebbian learning, which is being able to recreate neural circuits just by kind of going through the motions. So even if you don't do the motor control path to go from one place to another, just experiencing that movement can be useful. So one example is, I don't know, is anybody here a swimmer? Okay, well, in training very high caliber elite athlete swimmers, sometimes they drag them through the water really fast so they know what it feels like to swim fast. Obviously, that's not going to really help build the muscles required for swimming, but there's a neurological connection that starts to be made about how it's supposed to feel. And that can also be useful if you have sensory deficits and understanding what the movement should feel like given your new sensory situation. So assisting movement, while it has its problems, it can still be useful. And maybe the main advantage over a human therapist there is that a robot can do it over and over again without getting tired, and they can make sure to do it the same way over and over again. So challenging movement is kind of the opposite of assisting movement, and that is if I want to move from here to here, let's make it even harder for me to move. And that's a way of actually stimulating recovery and rehabilitation by pushing the patient, to recover these neural circuits, even more strongly than they would if they were just trying to make the movements without being challenged. And so the challenge that a robot can present is if you're holding on, or a robot is, say, holding on to your arm, and you try to move, it can create, say, a damping field. So it's like you're moving through molasses, so it's harder to move. Or you can be pushing against a spring. And so you can improve muscle tone, you can improve basically recreate the neural circuits that are getting lost. Simulating normal task gets into this task-specific side of things, and that's actually something that we're still very challenged to get robots to do. So let's say in simulation, let's say you have a virtual environment where you would like to practice doing certain things. And virtual environments can be nice in some way because they can be very controlled and they can be very safe. So So sometimes manipulating a normal object like this might be hard because maybe its surface friction properties make it difficult to grasp. But in a virtual world, you can make that friction very high so people can grasp those virtual objects and maybe do manipulation tasks that they couldn't do in the real world. But as you try to make those virtual environments in which people do these exercises more and more realistic, we have challenges in actually displaying to the user the kinds of forces that they should feel and just creating immersive environments that seem natural to a user. And that kind of gets to this issue of context. If you rehabilitate in a certain context, does that actually translate to the real world? So I have a collaborator who works on rehabilitation of walking, and so she has people walk on a treadmill. It's actually a split belt treadmill that adjusts people's gait, so you can make one leg go faster than the other. And so she tries to actually make it more challenging to walk, to force people to recover their movement. And then when she ties the belts together so they go at the same speed, people actually can then actually walk normally. So even though they didn't walk normally in the challenging environment, they could actually start to walk normally after practicing there. But as soon as they step off the treadmill onto the floor, the context where they did that learning and that training was lost, and then they start to walk with a deficit again. And so there's this issue of simulating normal tasks and being able to use, you could think of a split belt treadmill as a robotic device, but taking devices like that and somehow bringing them into the real world so people associate that context with natural behaviors and not, oh, it's just when I'm with this robot that I learn to behave differently. And the last thing I'll point out, which I won't talk much about today, is non-contact coaching. There are a lot of people in robotics who are really interested in using robots as sort of motivational tools for people. And the idea is that might be better than a computer screen because there's a physical entity. Maybe you feel more responsible to do an exercise when it prompts you versus if your iPhone just prompts you to do something. So, but I think I'm going to be talking mostly today more about physical assistance, challenging, and simulation. Okay, so I actually got the main topics for these slides from a researcher named Michael Vanderloos, who actually was a very close collaborator of Dave Jaffe's back when he was at the VA hospital as well. And he sort of breaks the field down into this historical pathway of the types of ways in which people have thought about creating rehab robots. And I'll just go through a couple of examples of each of these, starting from the first thing was replicating the therapist, like I mentioned earlier, all the way to enabling patients to kind of play a larger role in their own recovery. So the first phase, replacing the therapist, and I'll just give a couple examples of devices that were designed to do this. One of the first ones was created here at the VA hospital in Palo Alto, and this device called MIME, or Mirror Image Movement Enabler. The goal here was to allow a affected limb to simply follow the unaffected limb. And in a way, I mean, it did allow the patient to kind of create the desired movement, but it was really the patient kind of moving their own arm similarly to the way that a therapist might move a patient's arm. And it actually had a lot of different interesting modes of exercise, both passive and active. But the cool thing about it is this bimanual method where maybe this is the unaffected arm, and you would be able to sense the movement of that unaffected arm, and then the robot in this manner of assistance would help the other arm move. And so it was really just kind of taking a human input and mapping it onto how the affected limb would move. Probably, I would say one of the more successful commercial ventures, success in this field, the bar being pretty low, I think Dave will agree with me, is MIT Manus, which was a device that was then formed, a company was formed around it called InMotion, and it came out of MIT. And what this device did is just allow people to practice in virtual environments. So there's a patient who is just trying to hit different targets. This is a very classic center-out task. We go to the center, you just try to hit different targets, and it's a planar device, so you're only moving in 2 degrees of freedom. And the system would apply different forces to either challenge you or allow you to move. But again, it's not that different from the kinds of tasks that a therapist would actually help a patient with. And this is one of those systems that while it became somewhat popular and used in the clinic, there's not a whole lot of strong data to show that it helped patients more than a human. Another great, in some ways, in going through these different examples, I'm also going through the great centers of rehab robotics, and this is probably the most well-known of all, which is the Rehab Institute of Chicago, which collaborates closely with Northwestern University. And over the years, they've developed many, many rehabilitation devices. And this is an example that is kind of horribly big and clunky, but it allows people to make a lot of degrees of freedom of movement. And this is really important because so much work in both rehabilitation and neuroscience has been of the MIT Manus type, where you're just sitting around and moving in a plane. And again, it's about context, right? If you want to move people into doing things in the real world, well, they have to deal with gravity. The MIT Manus, you don't even have to support your arm against gravity. The robot supports you. And they're finding that people couldn't translate those simple 2D movements and lack of gravity support to doing something in the real world. So the hope in designing these more complicated, although horribly large and expensive devices, is that you could start creating environments where you have more degrees of freedom of motion, and that complexity hopefully would translate to better patient outcomes. So those are the sort of first types of rehab robotics that were developed. The next phase, which could be called augmenting the therapist, tries to do things that really no human therapist can really come close to by providing different types of environments. For example, a very functional task that's very important for recovery for lots of people is learning how to drive. And so this is a system also from the VA at Stanford, VA Palo Alto and Stanford. And this was actually done by a graduate student who was here at the same time I was, Michelle Johnson and collaborators. And the idea here is that you'd actually use a very motivating task like driving, which is not something a physical therapist can really help you, show you how to do. They can't really grab your arms and say, oh, pretend you're driving. Here you actually create this simulated virtual world that lets you experience a task that's important to many patients. And depending on how much movement they have, there are different control strategies for it. And I think those are on the next slide. Yeah, so what Michelle did was she designed a split steering wheel. So they're actually not connected on the two sides. That way you could separately measure and also control the inputs from the left and the right hand. And I didn't mention this, but for many stroke patients, but not all, there's going to be an issue just on one side of the brain or the other. And so you often have an affected limb and an unaffected limb. Although I have to say, there actually saw some recent papers that people think the unaffected limb is unaffected, but often there's some deficits there as well. So in any case, by splitting the steering wheel, then they're able to say, well, maybe we're going to ignore inputs from the strong arm and then force people to use the other arm more. So there are things that you can do in a virtual environment that you really couldn't do in a regular car, and that a therapist can't exactly do with a patient. Another example is this project. This actually comes from the European Union. It was actually a multi-institution collaboration. And you can see now, this is actually from the early 2000s, I think. Yep, 2001. So we're starting to be able to build kind of arm-based large movement devices that are not nearly as clunky as in the previous examples. And this system also allowed someone to experience some virtual environments, but now in lots of degrees of freedom, even including orientation as well as position. And one thing that this particular robot can do that human operators can't do is it can actually provide much larger forces. Now, when we talk about these devices that are coupled to human operators and then applying large forces, you always have to worry about safety. And the cool thing about this robot is it operated in a completely different control mode. The way most of these rehab robots would work is it would measure the user's position, and then it would actively create forces to push you in one direction or another. All this robot does is essentially create a brake that resists your motion. So it doesn't actively push you anywhere. It is controlled so that it is a brake in lots of degrees of freedom. And that's a more safe type of interaction for a patient. And it's also not really something that a human therapist can do. So for example, if someone is pushing on my arm and I'm pushing back and suddenly they let go, my hand is going to go like this, right? I can't stop pushing back so quickly. But this robot was really just a brake. So if someone's hand suddenly fell off it, it would just stay where it was. Okay, so safety is an important advent here. So the third phase is, which Mike Vanderloos calls designing the super therapist, to me is more about the strength of robots being connected to computers and collecting data that helps researchers and caregivers actually model the deficit and then target it more specifically. So this is a complicated set of plots, and I don't think I'll go through the whole thing, but let me give you the big idea. So what they had a stroke patient do is just try to move from one point to another. So their goal was to go from here to here. So all they had to do was make this reaching trajectory. But because of their movement deficits, they have a lot of strange movements that until they get to the target, sometimes they don't even reach the target. And I think the average movement here is shown in dark black, and then all the thin traces are examples of different movements that were done. So this is how the patient behaves initially. That's called the unperturbed baseline. And then there's this machine learning phase. This is where you have the super smart robot therapist. It actually looks at all of those deficit movements and says, well, I'm actually going to model that behavior. So although the patient has some variability, I'm going to look at their average behavior and I'm going to say, this is the deficit. There's a difference between how they're moving and what is the desired straight line. Now, if this was an assistive technique, you could then program the robot to help move the person in a straight line by applying the right set of forces. But rather than do that, they did this resistive or challenging technique, where instead they said, well, based on that average movement, I'm going to use forces to make the patient worse. So I'm going to make them exactly twice as bad as they were at the unperturbed baseline. And so then I'm going to make them practice the task over and over again, but worse. And so then you get this sort of behavior. So training, and then training. And then finally, what happens is we just then take away the extra forces that the robot's applying, and then you see what's left over. What has the patient learned by training in this more challenging environment? And then they get to this stage, stage E, where actually now they're making much more straight movements because they trained in this sort of smart environment that modeled that specific patient's deficit. And then they showed that later on in the training, the patient was actually able to hold on to the new type of movement that they learned. So this is actually, even though this was done quite a while ago, 2005, I have to say that this has not yet been successful in translating to more full body movements and all the degrees of freedom that stroke patients have to deal with in the real world. But it's promising that a robot can do something which a human therapist can't, which is to really quantify the deficit and then try to correct for it in a very rational way. And then just other examples for more immersive environments include a virtual world that you can actually walk through, whether you have to sit in a wheelchair or stand up. The idea is that you need to make the context be very natural so that what you learn with the simulator, the virtual world, can then be translated into real world actions. And then the last phase, and this is actually fairly recent, maybe the last 5 years or so, people are thinking about, well, we want to understand how patients are feeling about their rehabilitation and how can we target and understand that in order to optimize it. And so lots of studies recently have been looking at using affect, which is the understanding of the emotional state of the patient, in order to figure out what is the right way to approach rehabilitation. And there are many, many different models for affect, but here's some examples. So if you look at a plot of arousal versus valence, whether it's through biological sensors like skin galvanic response, the saltiness of the skin, heart rate, even questionnaires, they can say, oh, well, maybe a patient has low arousal and neither positive nor negative valence. That just means that they're sleepy. And so then a rehabilitation scenario should be targeted toward that patient's state to maybe wake them up and get them engaged in the rehabilitation. If someone is angry or annoyed, maybe you need to calm them down in order to be able to get them to continue with the rehabilitation practice. So one thing I thought I'd do here at the end of this part of the talk, I'm going to switch in a minute to talking about a specific research project example, is because I'm mostly an upper limb kind of person, and so all the examples I showed before were about upper limb rehab robots in virtual environments. So I thought I'd just give a couple examples of lower extremity rehab robots, because of course, when I actually first got into this field, I thought the first thing that patients would want to do would be to, reach for things and be able to, say, feed themselves and do personal care with the arms. But no, they really wanted to walk. Walking was the most important thing to most of the patients that we talked to. And so there's been a huge amount of effort. This is a very challenging field that's gone into creating walking assistance or resistance devices to help rehabilitate that component. And so I'll just throw up a couple of pictures. These devices are typically very clunky. They can't necessarily be used to walk around in the environment, unlike you guys had a speaker from Exos come in, right? And so that's an assistive system, not a rehabilitative system. So it doesn't have quite the same sorts of design goals, but we are still really, we need to get away from things that look like this to things that are more like the Exos for rehabilitation purposes. And this is kind of, Locomat is probably the best-selling, would you agree, David, the best-selling lower?
A bunch of that.
Okay.
We'll see one next week.
Okay. Is it still in active use there?
The problem is that it really doesn't, they really haven't done any studies to show it's really beneficial.
Yeah. So this is one of those commercially successful, as much as success can be in this field, systems, but as you can see, I mean, it's got a huge cost and major infrastructure changes to any location where you would actually put this in. So if you get a chance to talk to any of the therapists that have this over at the VA, you should ask them about it. Oh, fantastic. And then this is actually a great example from University of British Columbia, where it's a robot, but not specifically just designed for locomotion, but actually to look at addressing balance. And so balance issues is also a huge issue for many of these patients. And so they've looked at how people, recover from disturbances, because falls are, of course, very important to prevent in a recovering patient, because not only can they get injured, but it also creates a fear of a rehabilitation practice if a fall occurs. So by being able to study and give people actually a safe environment where they can deal with balance issues is also important. So what that was is just a quick overview of the field of rehabilitation robotics. I'm going to, in less than 10 minutes, is that good enough? Actually, just give you an introduction to something, a little deeper dive into an example of a rehab-related research project. And this is one that I did here and also at Johns Hopkins, and in collaboration with Amy Bastian, who's a neuroscientist at the Kennedy Krieger Institute in Baltimore. And in some ways, this isn't truly a rehab project, in that the type of patients that we're working with are very difficult to rehabilitate. Instead, we're using robots to understand their deficit better and then lay the pathway for future rehabilitation projects. So we were looking at patients with damage to the cerebellum, which is a particular part of the brain. It's, I think I have a picture here that's down here. And you can have cerebellar strokes, but often also patients, not often, but there are patients with genetic defects that actually result in damage to the cerebellum. And patients with this damage have a lot of trouble making movements at the same speed and accuracy as healthy people. And so if you have someone sit down in a chair and just try to move their hand to hit some targets, and you control how healthy people move, healthy controls, versus cerebellar patients, you can see an obvious deficit there. And my video wouldn't work today, but I can just give you a demonstration of one type of task that they do is the therapist will hold their hand out and a patient will have to do this nose to finger touch task. And I can do this very quickly and I can hit the target and I can move in a straight line. A cerebellar patient, if they're asked to move fast, they do this. They overshoot, they have some sort of movement corrections at the end, and they can do the task if they move very slowly. They can do the task. And so this has actually been a mystery for researchers for some time, is like, why could they do the task slowly but not quickly? And our hypothesis was that the patients don't know about their arms' dynamics. And when they move slowly, they don't have to deal with the fact that they're accelerating an inertia of the arm. When they move quickly, they do have to deal with that, and they don't know how. So this is some more examples of how these patients move. And the robot, again, it's not just a way to try to rehabilitate a patient, but it's something that enables us to collect data. So we're moving back here, unfortunately, away from real-world movements to just moving in the plane. And in fact, a lot of the movements we did were even a single joint movement. But here's a case where patients and healthy people had to move from a center point to some different targets on the outside here. And there's clearly a deficit going on here with the cerebellar patient, and also a little bit more variability if you look at some of the low-level joint sensors. The other thing that's really striking here is that there's not so much of a deficit in this reach here, but there are deficits in the other reach directions. And that actually lends more credence to the hypothesis that the dynamics matter, because it turns out moving your arm like this, less stuff has to move than if you have to move your arm in this direction, right? When I move it this way, you can see that both arm segments have to move. There's more coupling of the inertia between the different limb segments, whereas this is a much simpler movement. And you see the deficits in the locations where the movement is more complex. And when we do experiments like this, we ask the patients to move to the targets quickly. Because like I said, if they move slowly, they'll do okay. But we wanted to push them to move quickly so that we could see the deficit. And they sit in these exoskeleton robots. A much simpler exoskeleton than the Exos. It's just little planar manipulators. Okay, so to really look at this carefully, we did a study on single joint arm flexion about the elbow. And we took data on a bunch of both healthy people and cerebellar patients with cerebellar damage. So a typical control has to go from 0 degrees to 30 degrees, and this is how they move. Very smoothly, this is over time. They can move and they can hit the target, and then they can maintain it very well. So an interesting thing, and this has also been a bit of a puzzle in the community of cerebellar researchers, is that when you have a cerebellar patient do a task like this, some of them overshoot and wiggle and come down, and some of them actually, they undershoot. Like they don't quite get there, and then they recover. And so all of these little colored lines here are different patients and how they did. And then dysmetria is the, I guess, amount of error in the movement. And so hypometric patients have hypometria, that is, they don't move far enough. And hypermetric patients have hypermetria, they move too far. And for some reason, some patients are hypometric and some are hypermetric. And we also wanted to know why that was the case. So in our sort of robotics controls-minded thinking about how you solve problems like this, we said, well, we're going to actually try to come up with a model for this behavior. And I'll not go into this in detail, but the point is that this is actually a very basic control model. Some of you took E105 with me. You should look at this. Oh yeah, this is a feedback controller, and it actually contains a forward model. It's not nearly as complex as a lot of models that have been developed, of course, for movement control. And we purposely are trying to come up with what is the simplest model that could be used to describe human movement control. And on that model, can we test some hypotheses? So what we did to actually test our specific hypothesis, which now became that patients with damage to the cerebellum had a misunderstanding of the arm dynamics. So the thought was that the cerebellum is the part of the brain that houses a model of how heavy your limb segments are and how they're connected as well. And so if that part of the brain is damaged, then you're not being able to make fast, accurate movements because you actually, when you send a command to say, muscles, I want you to apply enough force or torque to get me from here to here, if you actually don't know how much weight you're moving, you're not going to do a good job. And if you underestimate the weight, that might cause the hypermetria versus the hypometria. And so to test that hypothesis, we built this model. We took healthy people, and healthy people are interesting because healthy people, well, they're great because they adapt. So I'm going to come over here and steal your drink here. If I pick this up, suddenly my arm is heavier, but I can quickly adapt to the weight in here and still make accurate movements. If I had to touch my nose and move this, I could still do this while I'm holding this. But a patient doesn't adapt. So for control or healthy people, we're able to use the robot to suddenly make their arm heavy or feel heavier or lighter than it actually is. And so we would perturb them and actually see how they responded and actually make healthy people look temporarily until they adapted like cerebellar patients. And then also compared this to a model that was developed based on this, and then compare that to data of how cerebellar patients actually move. And we had patients that had different reasons for their poor movement control. But the idea was that we had patients that have had a range of spectrum from ones that thought that their arm was too light to ones that thought that their arm was too heavy. And then finally, the cool thing that we could do is do a robot intervention where, just like with the healthy people, we used the robot to make their arm feel lighter or heavier and made them look like cerebellar patients, we can change the effective inertia of the arm of a cerebellar patient and make the arm therefore match the model that they have in their brain, which is wrong, but now becomes right because the robot has made their arm feel differently. And so when we do that, we can take patients that overshoot, who have hypermetria, and not perfectly for every patient, but on average move them down to have no dysmetria. And then patients that were the other way around, we can make the robot increase their inertia, again, to correct their movements. So this is not a long-term rehabilitation in that the robot is actually actively assisting them to make movements, but it helped us actually solve some unanswered questions about what is the role of the cerebellum in movement control, and then hopefully we can start to design therapies. So it's really answering a neuroscience question that will help us model the deficit and then create robots that are these super therapists. So the main conclusions of this research study were that we find patient-specific biases in the representation of dynamics in their brain. We can replicate it both in simulation as well as by perturbing healthy people's arm inertia with the robot. And then we can correct this dysmetria by effectively altering patient limb inertia using a robotic device. The key thing here is it doesn't correct variability, and so that part is still not something we can help patients with. So just to conclude, I'll note that in the big picture in my research lab here at Stanford, which not only does this kind of work with rehabilitation, but also with surgery, like I mentioned for my medical robotics class, is that the way in which robots can really be useful is when they use quantitative descriptions of patient state. So this first point here is that you can't sort of arbitrarily say, I'm just going to try this random strategy or something that's generally been used, but a robot's going to be most effective when it can acquire data that says something specific about that patient. And then you use those models to plan an intervention. And in this case, the intervention was actually changing the effective inertia of the arm. And then the robot itself is the device, the control, the process that connects that information to some physical action. In this case, changing the effective inertia of the arm by using the motors to apply extra torque or apply less torque to make it seem as if the inertia was changing. And then the human has to be able to use it and interact with it in a very natural way. All right, so I will stop there. And I don't know if you want to do questions now or at the end.
Take a few questions now.
Okay. Yeah, sorry.
Full scope of what the field that's all wants to reach.
Yeah.
So, is there
Yeah.
okay, we want to be able to
Yeah.
check box number one of it.
Yeah. No, I mean, I would say probably the biggest goal is to take a stroke patient and be able to optimize their treatment to get them back to being able to do the activities of daily living as quickly as possible. But that is so far away because we don't even understand why some patients recover faster than others. And actually, I'm part of a new big study here at Stanford that's enrolling a large cohort of stroke patients, and they're going to be looked at by different researchers, myself in movement therapy, but even people who are doing brain imaging studies to look at where damage is actually occurring in the brain and trying to kind of bring that all together. But that's almost like just a big data collection phase. And once we have that data, then the hope is we'll have a better model for what to do with it. Yeah.
Choosing control subjects,
there any kind of like screening? Maybe somebody was injured or something.
Yeah. No, that's a great point. Yeah, we definitely have to screen the control subjects for potential other deficits, whether they're just physical or they're neurological. The other key thing, and this can actually be challenging sometimes, is we need to do age-matched controls, and handedness match. So if we have a left-handed 50-year-old male with a cerebellar deficit, we try to find a 50-year-old left-handed male to do any statistical comparison against to characterize the deficit versus healthy behavior. And that can actually be challenging.
So in places where physical therapy is lacking, I'm thinking of a couple of developing countries.
Right.
Ones that I'm familiar with. How do you see this field sort of entering that kind of space where you have people who probably have just as high of likelihood of getting a stroke or anything like that?
Yeah.
How do you see this field entering that space?
Yeah, that's a great question. That is a huge weakness right now, and I would say not just here, but in all of robotics. The technology is expensive, it's not robust, it requires a lot of user training in order to set it up and use. It has huge power requirements. I would say, maybe I shouldn't speak for the whole field because someone out there might be thinking about it, but I really don't think people have thought at all yet about how to translate it into developing environments, because it still is at its neophyte stage in terms of working in developing countries. That's a great question.
Thank you, Allison.
Thanks.
Take a stretch while I sit.
Okay, I'll get that.
Okay, let's get going again so I can finish up. So I'm going to talk about assistive robotics, and these are robots that are functionally different than what Allison was talking about. These are just some images that I picked up today on the internet when I searched for assistive robotics, and I'll talk about some of these further on. This is one of my favorite ones. This is a robot that picks people up off the floor. Very useful, but this is the only picture in the world of it. Then there's robots that look like seals that help older folks as a companion, and talk about some others. So robots, we've seen robots every day. We've seen robots in the movies. We've seen robots as cars, as mechanical devices, and I added the Stanford self-driving car as a robot. But the most popular robot commercially is the Roomba robot. So they sold more of those than any others. In looking at robots, there's a lot of different kinds. Basically, it breaks down into things that are used industrially, things that are used medically. In medical, there are surgical robots, like the Da Vinci system. There's movement therapy robots that Allison talked about. And then there's assistive robots that can be broken down into things that help people at home, things that help provide walking assistance and prosthetics and exoskeletons, and then there's mobility devices. So in my definition, an assistive robot is a device that can sense, process the information, and perform actions that benefit people with disabilities or older adults in the course of their daily living. And there's all sorts of activities that we do daily that a robot can help us with. Some more pictures of things. So users of assistive robots include people with spinal cord injury, cerebral palsy, arthritis, older adults, people who've had stroke, ALS, muscular dystrophy, people that are temporarily disabled, amputees, and so on. And this robot is actually shaving this individual. And here's a robot from USC that is is like a athletic coach guiding this person to do exercise by matching the robot's movements. So some early assistive robots include this Rancho Golden Arm, and you can see it's like a exoskeleton for the upper limb, and it's actually mounted on a wheelchair. And looks like it's controlled by this switch near the person's mouth. Here's a John Hopkins one. You probably weren't around that early. So they actually took a prosthetic arm, they added a gripper to it, they added a bunch of ways so it can move on a surface, around the surface, and can be controlled by the user sitting at the desk here. A couple of things that we did at the VA many years ago is this MOVAR, stands for a mobile robot, and it uses these wheels that you might have seen on the Wii robot. These are Omni wheels, and 3 of them can move this robot in any direction. And I remember we did about an hour experiment where this was either voice controlled or controlled by head movements, and you can command it remotely. So we commanded the robot to move across a room and pick up a flower and return it, and that took about half an hour. But it worked. Really old technology. Another robot project that we had is looking at how we can make it help people on the job. So this is the same sort of robot hanging from this track here, so the robot can move along the track and pick up things like video discs. How many people remember video discs? Yeah. So a long time ago. And so this user is a quadriplegic. He's controlling a mouse, a trackball actually, and can command the robot by voice. Here's another follow-on project. Again, you see the robot on this track here. And the neat thing about this is that the user can program how to move the robot. So you basically move the robot to a position, and you can save that position, and then you can, by voice, have the robot move to that position rather than controlling each axis individually. So here's a student project. These are more current. These are articles that I've seen in the last year. Here's a student this is an emotive brain-computer interface going through his computer and controlling this robot arm here. So it's responding to brain waves. This is a newly introduced robot, the world's first family robot called Jibo. It's out of MIT. Cynthia Brezel worked on it. Really interesting. It's designed to be an attentive companion so you can interact with and will help you live with greater independence and stay connected to those you love. So we'll see if that actually works out. She got a lot of venture capital to make this happen, so it'll be interesting to follow their success on this. This is a robot that was built in China. It's hard to really see what it is here. It looks like sort of like an exoskeleton, but it has smoke and gas detectors and other things, so I'm not really sure what it can do, but they're really looking at it for elderly care in China. And any country that has a rapidly aging population really have to spend a lot of resources on caring for older people. Then there's these large robots that are designed for helping you out at home, whatever that means, and also keeping an eye out for older adults who can, because of this, they claim, can live independently at home. But we'll see how successful this is. This is a really cool application of a robot. This is the coolest one. So there's a guy who has apparently lost his hand and can't drum with one hand. So this is a robot that drums for him. So one of the drumsticks actually recognizes the beat of the music and follows along, and the other drumstick is controlled by EMG. So it's a very, very clever design. How many of these are they going to sell? Probably not very many, but it's an interesting project. Then there's all these projects with robots and kids, helping kids with diabetes and be more confident about their futures. These are all just a lot of claims, by the people who are doing this. So here's one that's for kids with autism. This is a smaller robot. It helps these kids' ability to engage socially. And here's a larger size robot that actually looks pretty scary, But people try these things, I've seen a bunch of these, and so this is in the transformer category. This is a Panasonic robot that can move a person around in what looks like a chair, but it can morph into part of this bed here. And getting a person out of a bed is a very difficult task, and if you can have a device do that, that's great. Another big robot called Pepper. It's a laser-guided robot, whatever that means. It's voice-enabled, so you can control it by voice, and it will speak back to you and relate to emotions. So how useful is that going to be? I don't know. This is a pretty interesting product, a self-steering robot cane. So it has cameras on here to detect obstacles. But, a cane's supposed to do that. I mean, it's supposed to, find obstacles with the cane or listen to reflections. But what's neat about this is it will find a free path and will let you, there's a wheel here that will prevent you from going into an obstacle. So it'll tell you what the free path is. So that's sort of interesting. And it has audio feedback as well. But, for people who are blind, you really don't want to interfere too much with their hearing. Otherwise, you lose that sense too. So that's, you have to watch out for that. So this is a project where they looked at using very soft materials to make the robot safer. But when you do that, you can't carry a lot of stuff. But they looking at it for washing, and this looks like a washcloth and feeding. But I'm not sure it'll pick up any food. But here's a device that will. Assistive device to help those who are unable to feed themselves. And this is on Kickstarter. And it's a bunch of servo motors, and it controls the spoon here. So it will feed you. But how many times have you wanted, gee, if I only had another hand. So these people at MIT, have two more hands sitting on your shoulder. So if you need another hand, that's great. So it's called supernumerary. And if you don't like extra arms being on your shoulders, how about around your waist? So these are all things that people are investigating. We'll see how well they work out. If you just need 2 extra fingers, here's a project that looks at that. And they say that it can be used to open the top of a jar. Vincent? Okay, that's Vincent's project. RoboGlove is a gripping exoskeleton, and it's really not made to be a rehab assistive robot, but maybe it can be applied there. Interesting. So here's a device that is actually a computer input device. It fits around the hand, and it basically senses, each finger, how much each finger is flexed. But they're saying here that instead of putting sensors on it, you can put actuators on it and maybe provide therapy to the fingers. So that's a very interesting concept. But it looks sort of fragile, though. This isn't a robot, but I thought I'd throw it in. It's a 3D printed prosthetic hand that can be used to provide these hands in developing countries. NASA's working on an exoskeleton, not for enabling people to walk, but by amplifying users' movements, giving them more strength and power. Honda has a bunch of really interesting projects. Here's one that apparently provides additional torque around the hip to help patients relearn how to walk by minimizing the force, the torque they have to produce around their hip. And here's a companion device that is actually connected to the ground, so it gives you a little push. So if you're going from a seated to a standing position or standing to seated, well, I'm not sure how you would sit with a device like this. So it helps you walk. But there's only one of these arms that goes down to 1 foot. You would think that would be symmetrical, that it would be symmetrical left and right foot, but apparently not. And this is my all-time favorite device. This is a Omni wheel on here. So it's a self-balancing unicycle that you can control just by tilting. So you're shifting your body weight, you can go faster, slower, and turn left and right. And so the idea for this was that this would be on the, you'd have it on in your car. So you'd park your car, and instead of walking a long way, to your final destination, you'd take this out of the car and sit in it, and you'd head out. And it's light enough to lift up. Really neat. It's been around for about maybe 8 years, but I'm not sure it's commercially available. But neat idea, right? I just saw this yesterday. 2 decades of refinement, the Carobot version 4. So each version of this they worked on at least 5 years, okay? So this one is modular. You can put it together in these modules. And it's sort of interesting to look at the head of this and the Jibo robot that I showed before. So you can add modules as you need to configure your robot the way you want. I wonder how many versions of this they'll actually have. So this is an obviously pretty crude robot that somebody built for a kid who doesn't have limbs. So these are the robot limbs here, very crude, pick up small everyday items. But on the other end of the spectrum, you have this device, which actually has a list price of $1,400, and it looks like it balances on 1 wheel, and it follows you along while you're shopping and you're doing all your shopping in Union Square. You don't want to carry your stuff. You really want to be fashionable, so you have a robot, chauffeuring you around. So that's sort of neat. A lot of these other social companion robots, which are basically a computer and a mobile base that you can interact with by touchscreen or speech recognition. So here's a telepresence robot that actually a kid used in school because he was injured. And the Exobionics exoskeleton, we don't want to pass that up. And finally, this is going to happen. This is a Cybathlon in next year, a championship for robot-assisted paraplegics, and you can only be a part of this competition if you use a robot prosthetic or exoskeleton. So able-bodied people cannot apply. So in summary, robots come in a lot of different forms, and assistive robots can be used in a lot of different ways. A lot of research being produced, but typically coming up with one-of-a-kind prototypes. And the very few assistive robots are in common use today. You can't go out and just buy one. There's no real... there's just a very limited amount of them out there. And why is that? Because they cost a lot of money, and their benefits really haven't been documented. So that's it. If anybody has any quick questions, I'll take that. Elaine?
I'm just wondering, how much these
Well, it depends, if it's a full robot or...
The Honda is free.
I don't know exactly. So you could look that up. Okay. Anybody else have any questions? I want to remind you to sign up for the VA tour on Tuesday. Sign up to meet with me. Make sure you sign the attendance list. Let me know if you have any questions. Thursday we'll have Gary Burke talking about prosthetics and orthotics. Thank you very much. Oh, look, I'm a minute and a half early.